Hello. In this video I'm going to walk you through steps for computing the slope, the intercept, and R-square value in simple regression. Although I'm going to be carrying out the calculations using Excel, I'm not going to be using the Excel functions for carrying out the analyses. Rather, I'm just going to be walking you through the steps associated with these formulas that you see over here on the right. So the aim is basically to give you a little bit clearer understanding about what is being computed when you are looking at your regression output. Nevertheless, I will include a link to this spreadsheet underneath the video description, so be sure to download it and check it out. So let's go ahead and start by talking about our data. So I have hypothetical data from 10 students who are measured on a variable x and y, with variable x denoting students' interest scores and variable y is denoting student achievement. So we have, for those 10 individuals, we have a measure of interest and achievement, and we are relating those two variables together. And the basic idea is that we are predicting student achievement as a function of student level of interest. You'll also see in our spreadsheet that I've already computed the means for x and y right here, as well as the standard deviations for those two variables. Now, before we actually start computing and going through the formulas for the slope and the intercept, let me just kind of draw your attention to the regression prediction equation. So this is our sample prediction equation, and this is what was called y hat, and this is basically the predicted scores on y for each individual, which are a function of the intercept for the regression line and the slope for that line. So basically we have the each person's predicted score on y is equal to the intercept plus the product of the slope for the line and their raw score on x. And what we're going to be doing is essentially trying to find the intercept and the slope for the regression line. Now you'll notice that below I've got just y, and this is basically stating that each person's raw score on y that we observe over here is a function of the predicted or fitted values on y plus prediction error. So let's go ahead and calculate the slope for the regression line. So I'm designating or denoting the slope as b subscripted yx, indicating that we're finding the slope for the regression line where y is being predicted by x. So in the numerator of this formula, you'll notice that within the parentheses we have x minus x bar and y minus y bar. So the x bar and y bar reflect the means for the x and y variables respectively. And what we're creating are deviation scores on x and deviation scores on y. So we're basically taking the raw score on x and subtracting the mean on x, and the raw score on y and obtaining and subtracting the mean on y as well. The next step basically entails computing the product of the deviations on x and deviations on y. And then the last step in the numerator is to sum those the products of those deviation scores together. The denominator is essentially computing the sum of squares for x. So we're taking the deviation scores on x, squaring them, and then summing. So let's go ahead and perform those operations. So I've got a column right here for deviations on x and deviations on y. So I'm going to start off by typing in equals the raw score on x minus the mean on x, and so that first observation is negative 1.3. We'll go ahead and do the same thing for the second one, and in this case I'm going to go ahead and lock the cell for the mean, and that way I can just compute this and drag it down, essentially grab it and drag it down, and then all the remaining deviation scores are filling in. I'm going to go ahead and do the same thing for y. I'm going to say equals raw score on y minus the mean on y. I'm going to go ahead and lock that cell that contains the mean, so that now I can grab this and drag it down, and there you go. So then the next step is to compute the product of those deviation scores. So I'm going to say equals deviation on x times deviation on y. And so when I grab this and drag it down, you can see that now I have the products. So the last step is where that sigma is, and it's just simply to sum up those products. So I'm going to go down here and I've got a little cell right here that's going to be reflecting the sum of deviation cross products. So I'm going to say equals sum, and then we are going to sum all of these values, and the sum of deviation cross products, which is our numerator in the slope formula, is 20. Now we have for the denominator we have the sum of squares for x. So for this we've already have the deviation scores on x, so we just need to square them. So I'm going to say equals, then we're going to take the deviation score for x, and then I'm just going to say caret 2 to say that we're squaring. And so that first case, the squared deviation score is 1.69. I'm going to grab this and drag it down so that now we have all of the deviation scores squared for variable x. And then we're going to sum up across. So I'm going to say equals sum. And now we have the sum of squares for x. So now we have the numerator, which is the sum of deviation cross products. The denominator is sum of squares for x. So now we can calculate the slope by just taking the sum of deviation cross products, placing it over the sum of squares for x, and it gets us a value of 0.45351. The intercept is a little bit less involved because it just entails calculating, substituting the mean on y, the mean on x into this formula, and then we already have just calculated the slope, which was the 0.45351. So I'm going to go down here to the intercept box that I've kind of established. I'm going to say equals mean for y, which is 5, minus the slope times the mean for x, which is this number right here, and that gets us 3.04989. So now when we substitute our intercept and slope into the prediction equation, this is what it looks like. So it's 3.0989 plus the 0.45351 times each person's raw score on x. Okay, so now let's calculate r square, and to do this we need to obtain sums of squares terms. We need to obtain the sum of squares due to the regression and the sum of squares due to the total, basically reflecting the total variation on y. So to do this, we are going to take our prediction equation that we've just generated with our intercept and our slope and essentially generate predicted scores or fitted y values for each individual observation. So the y hat is reflecting fitted y or predicted y values. So to do this, what we're going to do is we are going to go up to, for this first observation or first case, we're going to say equals, and then I've already calculated it, so rather than just typing it in, I'm just going to go down here where I've got the intercept, plug in the intercept plus the slope for the regression line, and now we're going to say times the person's score on x. So that's it right there. And so now when I hit enter, you can see that we get the first person's predicted score based on the regression model is 4.41043. Now I'm going to do this all the way down. So instead of doing this in the long way that I'm doing, I'm actually going to go ahead and lock the cells that contain the intercept and slope, and then I can just grab this and drag it down as well, and that way I get all of the predicted y values. The next step is to calculate the prediction errors, which is denoted as E, and another term is residuals. So in this case, we're going to take the person's raw score on y and subtract the predicted score. So to do this, we're going to say equals y minus y hat, and we'll hit enter, and so now we've got that person's residual. And so now we can grab this and drag it down. We do the same thing for each other person in our data set. Finally, over here we have the residuals squared. So in this case, we are going to take our residuals right here and we are going to square them. So I'm going to raise this to the second power right here, and there you go. And so now when I drag this down, we will now have the squared residuals. The reason why this matters is that part of the sum of squares total is sum of squares due to the residuals. And the fact of the matter is that we're trying to index variation or indicate the variation in y as a function of the regression and of the prediction errors. And if we sum up the prediction errors in this column right here, they would actually sum to 0. So to get around that problem, we are squaring the residuals, and then we are summing them up to get sum of squares residuals. And in fact, if you were generating output in SPSS or Stata or some other statistical program, you'll see that oftentimes you'll get an ANOVA summary table, and it'll have sums of squares in it. And so included are sum of squares due to the regression, sum of squares due to the residual, and then sum of squares total. So to obtain the residuals, the sum of squares due to the residuals, we are going to sum the values in this column. So right here, I'm going to actually type in equals, then sum, and then we're going to sum the squared values. So you can see that the sum of squares due to the residual within the model is 28.929 roughly. So to obtain the sum of squares regression, which is that portion in the numerator of our R-square formula, we take the predicted values on y, the y hat, and we are going to subtract the mean on y. And then we are going to square those. So to do this, we're just going to start off with equals, and we're going to take the y hat values, subtract the mean on y that we have right here, and I'm going to go ahead and lock this cell as well and drag it down so that you can see these values, and then we're going to square it. So in this case, we're going to say equals these values and raise to the second power. So we're going to do this for all of these. Okay, so now the last step then is to sum up those values in that column. So I'm going to go down here, I'm going to say equals sum, and we're going to add all of these values up. And so now we have the sum of squares due to the regression, sum of squares due to the residual. So the total sum of squares, it's additive, so we're just going to sum up these two values. So I'm going to say sum of squares regression and sum of squares residual, add them together, and we end up with a value of 38. So then the R square is really just easily computed as by taking the sum of squares due to the regression, placing it over the sum of squares total, and you can see that it's 0.23869. So finally, if you're like me, you like to check your work, and it's really easy to run this analysis using, again, some statistical program like SPSS or Stata. So I'm going to actually look at the output after running the analysis using SPSS. So you can see here, after running our analysis, the R-square value is 0.239, which is what we got right here. You can see that looking at the ANOVA summary table with the sums of squares, the sum of squares due to the regression 9.07, which is what we have right here. Sum of squares due to the residual 28.93, which is this number right here. The total sum of squares is 38, which is right here. When we look at the regression coefficients, the constant in SPSS output, that's the intercept, 3.05, which is the number that we calculated right here, and then the slope for the regression line, which is the 0.454 that you see right here, that's what we calculated there. So that is just a general overview of how to calculate our slope, our intercept, and R-square value using simple regression. And I hope you found this video helpful. Thanks for watching.